Alright, in this video I'm going to demonstrate how to solve for force problems involving coefficients of frictions. Here I have a box that is being pulled by a rope at, with a force of 50 newtons at a 53.13 degree angle. That's not exactly a random angle, that's what makes up a 3, 4, 5 triangle. Coefficient of frictions are stated. The coefficient of static friction is 0.4 and the coefficient of kinetic friction is equal to 0.2. That's just the comparison between the amount of friction you have for every unit of support. And so to say that coefficient of friction is 0.4, that's just saying there's essentially 4 units of friction for every 10 units of support. So we'll get back to that. I have right over here the results from our friction lab, and I'll just circle that here. And we've talked about it in great detail, but it's just important to know that there's really two situations when the object is moving. Constant motion or accelerated motion, if it's moving, the force of friction is constant. If the object is at rest with its system, then the force of friction is more of a balancing out force to maintain balanced forces. Alright, so to solve this problem, we need to have a force diagram. Now I'm going to skip the whole bubble diagram, although that is important, but we've got the gravitational force of the Earth pulling down on this object. I've got the tension force of the rope pulling at an angle, and I'm going to have some support from the ground. And I'm going to have some friction, and I'm going to assume that it's in this direction. It's not always in opposition to the force, but I kind of have to predict which way it must be to balance out those forces. Alright, so that's between the ground as well and the box. Alright, so I've got a force diagram. It's not exactly as neat as I wanted it to be, but you can do better. The College Board really wants a force diagram that has labels and then a vector diagram for analysis. And so this is my force diagram with label. My vector diagram, I'm going to use tip to tail. It doesn't matter the order you use. So I'm going to basically just slide things over. Now here's what I know. I know that the gravitational force is equal to m times g. If g is equal to 10, that's 100 newtons. It's given in the problem that the tension force of the rope is 50 newtons at that particular angle. If the hypotenuse is 50 and the angle is 53.13 degrees, that makes this one equal to 40 newtons. That makes this side equal to 30 newtons. In order to balance out the forces, the supporting force of the ground really just needs to make up the difference. If the Earth is pulling down with 100 and the rope is lifting up with 40, the ground really only needs to support 60 newtons here. This is an important calculation because when we determine the amount of friction, we need to know if we have enough friction to close the gap, basically to balance out the forces. So we need to make a calculation right here. So I'm just going to put a question mark right here because we have to do a test. The first test is to figure out what the max amount of friction we have with the supporting force. Now, if we have a supporting force or a coefficient of static friction that's equal to 0.4, like I said before, that just means I've got 4 newtons of friction for every 10 newtons of support. Now, this ratio is constant, so I'm going to use some proportional reasoning here. And if I have 60 newtons of support, I can use this comparison to figure out how much friction I have. So I'll just use X, I guess. Alright, now I'm just testing to see if I have the amount of friction. So basically, if this number is any number greater than 30 needed to balance out that vector diagram, then I know that I am still in the static state. which means that it's at rest. So I'm going to cross multiply. I've got 10 times x equals 240 newtons. Now that means that x equals 24 newtons. This number right here is not the amount of friction that I have. This is just telling me the maximum amount of static friction I have. And what I need to do is to determine if that is enough or a sufficient amount to balance out the 30 newtons from the pull from the rope. And it is not. So my first test is to test for static conditions. That condition failed. There is no way for me to balance out the forces if the maximum amount of friction I have is 24 newtons. So this whole situation is invalid because that requires a static state. I cannot have a static state because the forces cannot be balanced, which is necessary for an object to be at rest. So it must be moving. So I'm going to use the coefficient of kinetic friction. And this just means that there's 2 newtons of friction for every 10 units of support. Let me write this out because this is important, that meaning. We call it a coefficient, but really it's a comparison. It's a pet peeve of mine. It's bizarre. Alright, I still have 60 newtons of support. That hasn't changed. But the coefficient has changed, so the comparison has changed. Alright, now I'm just going to work this out pretty quickly because you guys can cross multiply just as good as I can. Equals 120. And 10 newtons, so x is going to equal 12 newtons of friction. Because it's moving, I had to use the kinetic coefficient of friction, and using that and the amount of supporting force that I have, I am able to determine how much friction I have. 12 newtons. Now that I've established that, I'm ready to solve this problem. I've established that I do have an unbalanced force, and that unbalanced force is going to equal the difference between 30 and 12, which is 18 newtons. So using Newton's second law, the unbalanced force equals mass times the acceleration of this system. That's 18 newtons to the right equals 10 kilograms times A. The acceleration is going to equal 1.8 newtons per kilogram. And the direction of that would be to the right, as indicated on the vector diagram. Hope this has been helpful. Thank you very much.